Welcome to another unit in this workbook, Statistics. This time I'm going to talk about the so-called hypergeometric distribution. With the hypergeometric distribution, we have a discrete distribution, and we could best illustrate this with the following example. Imagine we have a box with different colored chips. In this case, maybe 20 red chips and 60 of any other color. Now we're going to draw one of those chips. The chip is then checked for its color. Could be red or could be any other color. And once we checked this chip, we do not replace this in the box. So we keep this outside the box. So in other words, the distribution inside the box did change. In this case, I draw a red chip. So the distribution after the draw is that in a box there's only 19 red chips remaining and 60 of a different color. So the overall probability of drawing another red chip has changed. And that's actually the two indicators, or the two main indicators, of what a hypergeometric distribution is all about. It's drawing without replacement. So in other words, each element can only be drawn once and not more than once. Or the probability of drawing a particular type of, in this case, chip, of a particular event happening always changes after the event occurs, after, in this case, the chip is drawn. That was the general idea underlying the hypergeometric distribution. Now we're going to turn to the more mathematical aspects. Here we're going to start with the probability function, which for the hypergeometric distribution looks as follows. That's the probability that out of our sample of n objects, k objects will have the property, the characteristics we are looking for. Then, well, we have these three different parts. So what do the three parts actually stand for? Well, the k over k part, large K over small k part, is that out of the total large K red chips, there exists exactly k over k possibilities, possible combinations, that contain k particular red chips. Therefore, the last part is more or less the same, but from the different perspective. That's about combinations of non-red chips. So this is the overall number of red chips in the total box. That's how many red chips we want to have in our sample. That's the amount of total non-red chips in our box or in our population. That's the amount of how many non-red chips we want in our sample. And we divide all of this by this n over n, how many possible combinations of n chips that contain n particular, so of all n chips that contain small n particular chips exist. However, this can much easier be imagined as that's the total number of possible samples. While those are the definitions of these three parts, I would think about them slightly differently. That's all possible samples. That's the number of samples containing exactly k red chips. That's the number of samples containing exactly n minus k non-red chips. That's not a mathematically perfectly exact definition, but that's the best way on how to remember it. Well, in addition to the probability function, we can also talk about the two main parameters of a distribution, which are the expected value and the variance. Whereas the expected value is relatively straightforward, it's just the occurrence of an event or the probability of an draw of an element having a certain property times how many elements are drawn. So that's if I draw 100 elements. In my box, 20 out of 1,000 have this certain property, then 2% chance exists of drawing a particular element or an element of a certain property. Multiplied with the 100, I will get an expected value of 2. The variance is a bit harder to explain, as we can see here, but still the first part, that's pretty similar to what we get for the binomial distribution as well. This part actually represents the changes in the probability we've witnessed on the slide before. Well, that's then everything there is on the hypergeometric distribution from a theoretical point of view. So I hope you enjoyed this session. I say goodbye and see you next time.